Welcome to the sixth lecture of gravitation. This will be the last lecture of gravitation from irodov. Okay, after this we'll start with dynamics of solid body. Okay, if you like the videos, please do interact with questions in the comment section. Okay, suppose you have some doubt or you have certain ideas about this kind of thing, so please mention them in the comment section. Okay, I'll feel appreciated kind of thing, and more likely as a teacher, my main aim is to interact, means either you understood it or not, or those kind of things. Okay, so there are many Hindi channels kind of thing, and I too can speak Hindi, but this the name of the channel, as it suggests, okay, was specifically for bringing up the kids with English kind of thing. So those who are not that much fluent in Hindi kind of thing. Okay, so if you like the videos, do interact with them and do ask questions wherever you get stuck in concepts. Okay, so if you like videos, do like and subscribe also. Okay, just interact with the kind of thing. Just show me that you're studying or kind of thing. Okay, so let's start with the question. Okay, one more interesting thing. This question came in NEET something around 2 3 earlier. The variation of this question came in NEET. Okay, around 2017 to 18. Just see the papers. Okay, see now in this question there is moon. Okay, moon, and there is a satellite out here that is moving around moon. Now, if a satellite is rotating in an orbit, okay, suppose a circular orbit, what is supposed to happen? The satellite around a certain distance from moon has a orbital velocity v, and this will keep in a moving in orbit. Okay, now what happens is there is a lot of space dust. Okay, theoretically space is empty, but practically when you see, space is filled with lot of particles. Okay, even moon has a little bit of space dust flying around, or an atmosphere flying around. That atmosphere consists mainly of sand particles, and the density of this atmosphere is also very less. Okay, unlike our atmosphere, but it does have some atmosphere. It's not like completely empty. Okay, moreover, I'll say you call space empty, no? The density of space is around 1 electron per meter cube. Okay, I don't know. See, it's just authenticate the fact that I said. Okay, but the main point out here is space is not completely empty. There are some particles out here or dust cloud out here. Now, in this question, it is given that due to this dust cloud around moon, okay, the satellite that is revolving around this orbit experiences the drag force. Okay, drag force is nothing but air friction force. Okay, this satellite experiences a drag force, and that drag force is given by a v square. Where I'm drag force is equals to a v square, where a is an constant, v is nothing but velocity of the satellite. Okay. Now, whenever a tough question comes, what did I say? What are the two main things you have to do? The situation and the equation. Okay. So let's figure out the situation first, then we'll move on to the equation. Okay. So the first thing is every orbit has an orbital velocity. What do I mean by that? Suppose a satellite is out here in this orbit. Okay. The orbital velocity of the satellite is nothing but gm mass of moon divided by r. The orbital velocity in this orbit is nothing but under root gm by r. Fair and fine. Now, if the satellite is moving with orbital velocity, it will keep moving in a circular orbit without any hindrance. Fair and fine. Somehow, if the satellite or if the velocity of the satellite is increased more than the orbital velocity, what will happen? It will move away from the parent body. That means it will make a bigger orbit. Okay, more increase in velocity, more bigger orbit. More increase in velocity, more bigger orbit. And somehow, if the velocity of the satellite is lesser than the orbital velocity out here, what will happen? The satellite will move towards the parent orbit. That means it will deorbit. Okay, it will make a lesser orbit, then it will make a more lesser orbit, and then it will make a more lesser orbit. So every orbit has a fixed orbital velocity. If the body in an orbit has velocity greater than the orbital velocity, it will move away from the orbit. Okay, or it will make a larger orbit. If the velocity at this point or at the orbit has velocity lower than the orbital velocity, then it will move towards the planet. Or it will make a smaller orbit and smaller orbit until it matches with the orbital velocity or falls to the surface of the planet. Understood this much? Okay. So because due to this friction force, the velocity of the satellite out here reduces. And when it reduces, what happens? The satellite deorbits a little bit. Okay. Now when it goes out here, see, the actual motion of the satellite would not be circular. Okay. It will be something like spiral. Why? Because when it moves out here, the velocity is reduced, so it deorbits. So it deorbits somewhat like this. Again, deorbits somewhat like this. Because the force or the drag force is continuous in nature, no? So the satellite will keep deorbiting until it reaches to the surface of the moon. Okay. It reaches to the surface of the moon. Fair and fine. Now you have to find out the time taken by the satellite to reach the surface. And how do I do that? Find out time taken or how long. Okay, find out time taken. Okay, so you figured out the situation of what is happening out here. Now let's go to the equation part. Okay, what are the variables we have? What are the parameters we have? What are the parameters we need? We need a parameter of time. Okay, we need a parameter of how much? Parameter of force is given. Force is equals to av square. Okay, so velocity is there. Fair and fine. Radius is there. See, the radius of the satellite out here is n times radius at the surface. That means what? If the radius of moon is r, okay, the radius of satellite from the center of moon is nothing but nr. This is given. So you also have the radius out here. Radius. Okay. Okay. We have these variables. We need to find out the value of time. Okay. So we understood the situation. The velocity is being reduced by the drag force, and somehow it is deorbiting to form into the moon. Okay. How do I construct my equation out here? The first thing is with this velocity or with this range of motion, okay, tangential range of motion, can I construct an equation? Force is equal to mass into acceleration. Okay. So from Newton's law of motion in tangential direction, okay, force is equals to mass into acceleration or tangential acceleration. Tangential force is equals to mass into tangential acceleration. Fair and fine. Okay. Let's see what is yields us. What is the tangential force? Tangential force is nothing but av square. Okay. Mass is nothing but mass of the satellite. Tangential acceleration can be written as dv by dt. Okay. Or rate of change of velocity. Fair and fine. Now we got a parameter of time. Okay. Now somehow I need to find out a gravitational parameter. That means what? Av square is equal to dv by dt. There is one more force acting out here, no, on the satellite. That is the gravitational force due to moon. So somehow I have to introduce a parameter of gravitational force in this equation. Okay. And how do I do that? See, look very carefully out here. Okay. Or let's solve this parameter first. Av square is equals to m dv by dt. Okay. Dt is equals to m by a dv by v square. Okay. And if I integrate this from 0 to t, okay, from time t is equals to 0 to time t is equals to t, with initial velocity, that means velocity at out here, and final velocity being velocity when it touches the surface. So initial velocity is nothing but vi, final velocity is nothing but va. So time taken is equals to mass divided by a into dv by d square is nothing but v to the power minus 1 by minus 1, v to the power minus 1 by minus 1, v initial to v final. Okay, or time is equals to m by a minus m by a 1 by v final minus 1 by v initial. This much we know. Okay, and I actually now I have a problem out here. Okay, the problem is I have run into equation where I need final velocities and initial velocities. That means final velocity out here and initial velocity out here, and I don't have anything to deal with velocity. Okay, I do know the initial radius and final radius. I do know the value of g. I do know the mass of moon. But using those, I need to find out final velocity and initial velocity. That is my problem. Okay, or time is equals to minus m by a 1 by v final minus 1 by v initial. Okay, so this is my first equation. Now for the second equation, okay, I do need the terms of velocity. No, that means I cannot use the variable of velocities out here, isn't it? So to introduce a term of velocity, to subtract this variable velocity out here and replace it by g and r. Okay, I'm substituting this variable v by g and r. Okay, what do I know? See, it started out here with some orbital velocity. Okay, but when it reduced, okay, when it is reducing in velocity and deorbiting, that means when it is going like this and when it came out here, okay, out here also, if the velocity, okay, out here suppose the satellite is moving with certain velocity, okay, if that velocity is the orbital velocity, it will keep moving in a circular orbit. If that velocity is lesser than the orbital velocity, it will go towards the planet. Okay, if that velocity is greater than the orbital velocity, it will deorbit, isn't it? So when it is coming out here, what is happening is, see, the friction drag forces or the drag forces is very low. Okay, so out here it is orbiting like this only. Okay, that means when it reached out here, or when the satellite came in this spiral path and reached out here, the velocity of the satellite out here is nothing but the orbital velocity of this orbit. Okay, if this orbit was a circular orbit. Okay, then again it experiences some amount of drag forces, and then again it deorbited. Slow deorbitation. Okay, similarly, the velocity of satellite out here is the velocity of this orbit only. Understood? So the velocity of satellite at each point in the spiral is the orbital velocity at that point, isn't it? I know this much. Okay, that means velocity out here. Let me check. Velocity out here of the satellite is nothing but the velocity of this circular orbit. Velocity of the satellite out here is nothing but the velocity of this circular orbit. So at every point, until it touches the surface, even at surface, before colliding with the surface of the moon, okay, the orbital velocity of the satellite would be nothing but under root gm by radius of moon. Understood this much? Okay, because this is slow orbitation, slow deorbitation. That means the deorbitation is being very slowly. Okay, fair and fine. So at every point in the spiral, the velocity of satellite would have its orbital velocity. Okay, so v is equals to, let me write down the point that I said right now. At every point in the spiral, at every point in the spiral, the satellite would have the orbital velocity. The orbital velocity of that point, of that orbit, or of that point. That means out here, okay, when the satellite is out here, the satellite will have an orbital velocity of this orbit, okay, not the large orbit. That means out here, this orbit. Instead of going spiral, make a circle out here. Understood? So at every point in the spiral, the velocity of the satellite will be an orbital velocity. Okay. So if I know that every point in the spiral, the velocity would be an orbital velocity, I also know that that velocity would be nothing but v is equals to under root of gm by capital R, where R is nothing but the distance of the satellite at that instant, isn't it? Isn't it? Suppose I know when it collides with the moon, okay, the velocity is nothing but under root of gm by R. Okay, so final velocity is nothing but under root gm by radius of moon. Initial velocity is nothing but under root gm by this much distance. Understood this much? This much should be understood. So we get from our equation that final velocity and initial velocities are nothing but gm by radius of moon and gm by n into radius of moon. Okay, this is the thing that is most important out here. After that, the question itself is solved. Okay, so out here in this equation, final velocity is nothing but gm by radius of moon. Out here will have final velocity, no? Final velocity would be applicable out here. So final velocity is nothing but under root of gm by radius of moon. Okay, and initial velocity is nothing but under root gm by this much distance. Okay, this much distance, and this much distance is nothing but n times the radius of moon. So initial velocity is nothing but under root of gm by n into r. This much is understood. Okay, these two parameters and this equation you have understood. How did I get the time? Now I just need to solve these three equations. This equation, okay, and these two equations to find out the time required. And now from now on we'll just focus on to the equation solving. Okay, one more thing. Okay, this value of gm by r can also be written as gm by r. Okay, gm by r square is nothing but acceleration due to gravity at the surface of the planet, isn't it? So can I write gm by r is equals to acceleration at the surface into capital R, radius of the planet. So this gm by r can also be written as gr. So v final can also be written as under root of gr, and v initial can also be written as under root of gr divided by under root of n. Okay, so in some books you'll find the solution in terms of gr, okay, small g into capital R. In some books you'll find the solution in terms of gm by r. So do not get confused about those. Okay, the method in both the books are somewhat absurd. Not both means. Okay, I won't go into details of those things. Okay, means I'll just suggest apply your concept logically. Okay, don't bring out variables. If you see a variable, doesn't mean that equation will correspond to that variable. There is concept also, no? So just apply your equation conceptually. Don't go by whatever works. Okay, you might find the correct solution, but that doesn't mean the concept out there is right. Okay. Okay. So what was I need to substitute this thing or these terms out here. Okay. Now I just need to substitute these values, okay, out here. So if I substitute v final is equals to under root of gr and v initial is equals to under root gr by root n, we get something like this. Okay, this is the first thing we'll get. Okay, fair and fine. Now see, after that I can take root gr by common. I'll get something like minus m by under root gr 1 minus n. So I'll get something like this. Okay, and if I multiply this minus by minus inside this bracket, I'll get the main answer that is given. Okay, fair and fine. Now see, one more. In some books, okay, the answer is given as m by a, okay, under root gm by r, gm by capital R, okay, into under root n minus 1. This term and this term are the same thing, okay, because this under root of gr is written as under root of gm by capital R. So both the solution or both the answer or both the terminologies of the answer are the same thing. Okay, that's it. So in this question, you have to find out the orbital velocity and escape velocity from the moon. Okay, we already know that orbital velocity from the surface is nothing but gm by g mass of the planet by radius at the surface, isn't it? And v escape or escape velocity from the surface is nothing but 2gm by capital R. You already know these two values from our classes, isn't it? And how are these two values derived? This one is derived from g or gravitational force divided by r square is equals to amv square by r, isn't it? And this one is derived from total mechanical energy at the surface is equals to total mechanical energy at infinity. So if a body is projected with escape velocity, so total mechanical energy at the surface is nothing but half m into v escape square plus minus gm m by capital R is equals to the kinetic energy when the ball reaches at infinity is nothing but 0. That means the body loses all its velocity plus potential energy at infinity is already 0, isn't it? So using this equation, we obtain the escape velocity. Using this equation, we obtain the orbital velocity. And the relation between orbital velocity and escape velocity is nothing but, okay, v orbit is root 2 times v escape. Okay. Sorry. See, this can be written as, v escape can be written as root 2 into gm by r, and gm by r is already orbital velocity. So escape velocity is nothing but root 2 times orbital velocity. Okay. Now these are the only three formulas you need to use. Okay. And using those, we'll find out the values of orbital velocity and escape velocity. See, the mass of the moon would be given in the question, okay, or whatever parameters that are required would be given in the question. Few things, if you keep in your mind, it will be very helpful. The acceleration due to gravity on the surface of the moon is 1/6 time the acceleration due to gravity at the surface of the earth. That means g moon is nothing but g by 6. Okay, moon is 81 times has lower mass than earth. That means mass of earth is equals to 81 times the mass of moon. Okay, there are a few things you need to remember, okay, inside your syllabus. Rest of the data would be given in your syllabus. Okay, so orbital escape, plug in the data, find the answer and divide them or compare them. Okay, so these are the question number 2 to 8. So in this question is a little bit difficult to understand. Okay, so I'll explain this question in simple language. So there is moon. Okay, now a particle is coming from infinity in a parabolic path, and when it passes over the moon, okay, suppose a particle was coming from infinity, okay, and when it passes over the moon, if nothing happens, okay, it goes back to infinity. Any particle that comes from infinity encircles a planet due to the force of gravitation and goes back to infinity. Okay, that is the point. Okay. Just one concept out here. What is the velocity of the particle out here? Okay, the velocity of the particle out here would be nothing but escape velocity. Why is that? Velocity of the particle out here would be nothing but escape velocity, 2gm by capital R. Okay, and sir, why is that? Why is the escape or why is the particle out here with escape velocity? Why is it not less than that? If I just see the half section, okay, if I just draw a half section out here, now assume a different scenario, okay, moon. Now there is a satellite out here. What is the minimum velocity that I must give this satellite in this direction so that this satellite escape from the influence of the moon or gravitational influence of the moon? The minimum velocity is nothing but the escape velocity. Understood? 2gm by r. and he escape in a manner going a parabolic path. Okay, and in this parabolic path, the value of eccentricity is equals to 1. Okay, so when the value of eccentricity becomes 1, that means what? The satellite or the body, okay, escapes the orbit of the planet. That means it's no longer under the influence of the gravitation of the planet. Understood? This is the main concept out here. Okay, now there is one more thing. Okay, how did I obtain this? Total mechanical energy at infinity is equal to total mechanical energy out here. Okay, if you do that equation, you get the velocity to be 2gm by r. Fair and fine. You might also get a wrong idea from this equation. The wrong idea that you might get is that escape velocity depend upon direction of projection. Okay, that is not the case. Okay, escape velocity does not depend upon any direction, or escape velocity do not depend upon the direction of projection. Depend on the direction of projection. Direction of projection. Yes, I'll discuss this statement later on. Okay, just what this statement means is, whenever you're talking about escape velocity, that means suppose you throw this ball at any direction. If the velocity is greater than this 2gm by r, that means this ball will escape the gravitational influence of the planet. Okay, this ball can be thrown in any direction. As long as the velocity is greater than this value, it will escape the gravitational influence of the planet. Okay, escape velocity does not depend upon direction. Out here, the parabolic path means with the value of eccentricity e is equals to 1. The planet came out here and it will be going back to infinity. Okay, imagine sometimes earlier I told you, how do you launch a satellite? You take it to orbit, it keeps rotating in orbit, and then you increase the value out here, or increase the velocity out here. It goes in an elliptical orbit, you increase some more velocity, it goes in a more elliptical orbit. After a certain time, what happens? When the value of eccentricity becomes 1, it escapes the gravitational influence of the planet. The same thing is happening out here, but in reverse order. Out here, we're expulging an object from a planet. That means we're removing an object from a planet by giving velocity. Out here, the velocity of the planet or velocity of the body that is orbiting the planet is already from infinity. Okay, this came from infinity, we rotate out here and go back to infinity. Okay, understood the situation of what is happening. Okay. Now the question that is being asked is that, what is the change in velocity out here? That means we have to reduce the velocity of the satellite out here by such an amount that instead of escaping back to infinity, it will keep on rotating around moon. Okay, see, out here the satellite came. Now by firing a lot of thrusters or rocket, what I'll do is I'll reduce the velocity out here, and I'll reduce the velocity in such a way that it keeps rotating around moon. Okay, so let me delete this one. So after coming out here, moon out here, if no change in velocity was there, what would happen? The body would escape back to infinity. But I must give it a velocity, or I must reduce the velocity by a certain amount that it keeps on orbiting in this circular orbit at the surface of the moon. Okay. Now, can you guess what the velocity out here is so that this body keeps on orbiting the moon? This is nothing but the orbital velocity out here, isn't it? Orbital velocity, gm by r. That means when the body came out here, we have nothing but the escape velocity. Okay, and I must reduce its velocity by such an amount that the velocity becomes the orbital velocity. The question is asking how much of the spaceship velocity modulus increased in the process of braking. Okay, that means this velocity or escape velocity minus orbital velocity. That means this was the original velocity, this was the velocity that I have to bring down the satellite into, okay, by braking. So change in velocity or delta v is nothing but the initial velocity if nothing was done. This is nothing but under root 2 gm by r minus what is the velocity that I must bring the particle to so that it keeps on rotating in this orbit and the surface. It is nothing but under root gm by r, under root gm by r. So the amount of velocity that I have to decrease is nothing but I'm taking gm by r common into root 2 minus 1. Root 2 minus 1. Understood? And this is our answer. This is the amount of velocity decrease that I have to apply to the satellite to keep it orbiting around the moon. This is the entire parameter of the question. Okay. Now this question is the exact opposite of the previous question. Okay. Out here, the question is saying there is moon, okay, or there is earth. In the previous question it was moon, in this question it is earth. a satellite is rotating at the surface of Earth. Okay, if this satellite is rotating at the surface of Earth, what is the velocity out here? The velocity out here is nothing but the orbital velocity at the surface under root gm by r, isn't it? What additional velocity I must give this satellite such that it escapes the gravitational influence of Earth? Okay, so the velocity after outer velocity is under root gm by r. So I increase by velocity of by a certain amount. Okay, I don't know that amount, but the final velocity of the particle or minimum required final velocity of the particle to escape the influence of the Earth is nothing but under root 2 gm by r, isn't it? The escape velocity, and it will escape like this in a parabolic path. Okay, and the question is asking what is the changing velocity? The same thing, or delta v is nothing but velocity escape under root 2 gm by r minus under root gm by r, or delta v, amount of velocity that is given to the satellite, is nothing but under root gm by r root 2 minus 1. Same as previous question. In the previous question, it was talking about moon. In this question, we'll talk about Earth. But m is mass of Earth, r is radius of Earth. But that's it. Okay. Now in this question, okay, there is moon out here, and there is Earth out here. Then fine. Very near to the moon, the gravitational force due to the moon would be far larger than the gravitational force due to the Earth, isn't it? And very close to Earth, the gravitational force due to Earth would be much larger than the gravitational force due to moon. Somewhere between these 2 points, at a certain point, there might exist where the gravitational force due to Earth is equal to the gravitational force due to the moon. We have to find this point from the center of moon. Okay, the distance between centers is, we have to find out what distance from the center of the moon. That means we have to find out this distance x. Okay, from the center of moon. And at this distance x, the gravitational force due to Earth is equal to the gravitational force due to the moon. And then only the field outlet becomes 0. That means field means what? Force on 1 kg of mass, isn't it? Okay. So given in the question, the distance between the two planets, or center to center distance between the two planets, is given as 60 r, or 60 times the radius of Earth. Okay. Mass of moon is, if m, mass of Earth is given as 81 times the mass of moon, and m is nothing but the mass of moon. Okay. So F of Earth, or force on 1 kg, or gravitational force on 1 kg at this point due to Earth, is nothing but g, mass of Earth 81 m, into 1 kg of block. Applying the force on 1 kg of block, no, because field is nothing but force on 1 kg at that point in space, into 1 divided by r square. What is the value of this r? The value of this r is nothing but 60 minus x, isn't it? This much distance is nothing but 60 minus x. Okay, so 60 r minus x whole square. And gravitational force on 1 kg due to the moon is nothing but g into mass of moon into 1 kg divided by x square, isn't it? Or this much distance square. And at this point in space, this force is equal to this force. So I can say what? This value, or g into 81 m divided by 60 r minus x square is equals to g into m divided by x square. M and g and m will get cancelled. Okay, or I'll get somewhat equation like this. Okay, now if I invert both left hand side and right hand side, I'll get something like 60 r minus x whole square by 81 is equals to x square. Okay, 81 can be written as 9 square, because 9 into 9 is nothing but 81. So I'm writing 81 as 9 square. So my equation will be nothing but 60 r minus x by 9 is equals to x, and I have to find out the value of x. Or 60 r minus x is equals to 9x. I'm multiplying this 9 on the right hand side, 9x, or 60 r is equals to 10x, or x is equals to 60 divided by 10, nothing but 6 into r. Okay, so this x is nothing but 6r. Distance of the point for the gravitational force or gravitational field is equal to 0 is nothing but 6r from the distance of the moon. Okay, and the remaining distance is nothing but 60 minus 6, is nothing but 54 R from the center of Earth. This is our question. Okay. Now, if you want to, acha, acha, this question is very much simple. Out here there is Earth, and out here there is Moon. Okay. Now a spaceship is out there on the surface of the Earth. That means this is a stationary spaceship. Okay. What is the minimum amount of energy that I must give this rocket so that it goes to the or it reaches the moon? Okay, it reaches the moon with soft landing, the hidden part of the question. That means out here. Okay, if I just throw it to the moon, I'll require much less energy. I'll tell you in a detailed manner. But the necessary scenario in this specific question is it starts with zero velocity and it reaches the moon with zero velocity. Okay, that means soft landing on the moon. The question is saying soft landing on the moon. Soft landing on moon. Okay. Okay. So I can simply apply work energy theorem, where work energy theorem states that change in kinetic energy is equals to work done by all forces, isn't it? Now, what are the two forces out here? The two forces out here are nothing but the gravitational force, okay, and the propulsive force. Propulsive means the rocket is fueling some exhaust gases, With the help of exhaust gases, the rocket is traveling. And that kind of propulsive force out here is known as external force. So you have to find out the work done by external force or work done by propulsive force. Understood the question? So out here, two works are there. Work done by gravity forces plus work done by propulsive force. And this work done by propulsive force is the thing that we have to find out. Okay. Or work done by external force. Okay. What is the final kinetic energy when it reaches the moon? Zero. Soft landing on moon, isn't it? What is the initial kinetic energy? Zero, because it started from Earth. So final kinetic energy minus initial kinetic energy is equals to work done by all the forces. What is the work done by gravitational force? Minus of final potential energy minus initial potential energy. What is final potential energy? Minus of final potential energy minus initial potential energy plus work done by propulsive force or work done by external force. And this work done by external force is our question asked. Okay, or work done by propulsive force is equals to final potential minus initial potential. Okay, what is the final potential? The final potential, that means when the rocket reaches the moon. What is the final gravitational potential? Gravitational potential due to moon plus gravitational potential due to Earth. The final potential is nothing but minus g small m. Acha, mass of moon. Let's say mass of moon is m. Or let me denote mass of moon by any other parameter, okay? Any other variable o, x and y, okay? But x is mass of moon, y is mass of Earth. Okay. Gx by radius of moon. Okay. Let r be radius of moon. R is nothing but radius of moon. And capital R is nothing but radius of Earth. Okay. So final potential out here is nothing but potential energy due to moon plus potential energy due to Earth. So minus gy by this much distance. Okay. Let this much distance be a. Okay. Minus initial potential energy. Initial potential energy is nothing but, what is the potential energy out here? Minus g into mass of Earth by radius of Earth minus potential due to moon. Initial potential is nothing but potential due to Earth plus potential due to moon out here. Okay, minus gx by a. Okay, the one more assumption in this question out here is that distance a is very large. Okay, one important assumption out here is distance a is very large. So out here we make these terms to be 0. So work done by propulsion is nothing but minus gx by r minus gy by capital R. Okay, or work done by propulsion is nothing but minus g. What is x? X was nothing but mass of moon. G into mass of moon divided by radius of moon minus g into mass of Earth divided by radius of Earth, where y was nothing but mass of Earth. and capital R is nothing but radius of Earth. So this is our answer. If I want to modify this answer, it would be nothing but if I take minus and g common, it will be nothing but minus g mass of moon by radius of moon plus mass of Earth by radius of Earth. So this is the question. Okay, one more thing. I have to multiply this entire thing by mass of satellite. Okay, because work done is nothing but mass into potential or mass into change in potential. Okay, so I have to multiply this entire answer by mass of satellite. That's the thing. Now look out here. Okay, the thing that I said out here is a little bit wrong. The answer itself is correct. All the assumption I took is correct, but the solution that I took is very oversimplification of the actual thing that was happening out there. Okay, now I'll just discuss what was the real thing or what conceptually how this is the answer. Okay, so suppose there is a planet or suppose there is Earth. Okay, have you done that question? Draw the graph of potential from the distance of the center. And how does the graph look like? The graph somewhat looks like this one up to radius r. Then after radius r, it will go like this. And in this graph, potential versus potential in y-axis versus radius from the center in x-axis. Okay. In this graph, what you have done is I have taken the magnitude of the potential. But if you take the sign also of the potential, the graph will somewhat look like this, isn't it? The graph will be mirror of what was out there, isn't it? This is the graph of potential versus distance from the center of the Earth, isn't it? Graph of potential energy versus distance from the center of Earth. Fair and fine. And we took only that on x-axis. Suppose you have to take in negative x-axis. That means suppose I'm going this way or in this direction. What is the value of potential? It will be same but mirror of whatever there is in right hand side. That means this graph will just mirror itself on the left hand side, isn't it? Because if you go either left, not this one. Actually, I've drawn the radius out here very far away. The radius out here should be out here. The radius of Earth. This is the radius of Earth. Okay. Okay. Understood. Now this was the graph of potential versus radius from the Earth, isn't it? Now what happens if I take another body or another mass at some distance from Earth? Let's say moon. Okay. How the combined potential graph look like from the origin? See, the combined potential would look somewhat like this. Okay. Out here moon. Okay. Radius of moon. And inside the radius of moon, the graph would be somewhat like this. And outside the radius of the moon, the graph would go somewhat like this, isn't it? To infinity. And in between them, there will be some point where the graph goes somewhat like this. Okay. Now, do I have to memorize this graph? No. But this graph is actually drawn by computers. Okay, you plug in the equation into computers and they will give you a graph of potential versus distance from the center. And the equation that you use is nothing but potential is nothing but g mass of Earth divided by distance from the center plus g mass of moon divided by distance from the moon at every point. Okay, at this point, suppose I find out the potential at this point, do nothing but g mass of minus into g into mass of this distance from Earth minus g into mass of this distance from moon. And using this potential, we plot the graph, this graph. That means at every point, the potential energy is nothing but this value of z. Okay. Now, what is the potential at this point? The potential at surface of Earth. The potential at surface of Earth is nothing but g into mass of Earth minus g into mass of Earth divided by radius of Earth, isn't it? G into mass of Earth divided by radius of Earth minus g into mass of moon divided by this distance from moon. Okay, center to moon to surface of Earth divided by this distance of moon, or let that be whatever distance. Okay, at the surface of moon, what is the potential out here? That means at the surface of moon, what is the potential out here? At the surface of moon, the potential is nothing but minus g mass of moon divided by radius of moon minus g into mass of Earth divided by surface to center of Earth, isn't it? Surface to center of Earth. Okay. Now in the question, it is assumed that this distance or distance between Earth and Sun, sorry, Earth and Moon is very large. So ignore this kind of, or ignore these two terms. These two terms would be 0. Now the question becomes much simpler. A body is kept at the surface of, or the satellite is kept at the surface of Earth. What is the minimum energy that I must give it so that it reaches the moon with 0 velocity? Okay, that means what? Out here, whatever is the potential energy, I must first bring the satellite out here, no? Or a satellite to a point where there is maximum potential, and the value of that maximum potential is very nearly equals to 0, isn't it? And at that point of maximum potential, I'll tell you one more thing: the field also becomes equals to 0. Okay, you have done those somewhere. At between this Earth and Moon, there exists a certain point where gravitational field is equals to 0. That exact point is the point where potential is also maximum, or the value of potential is also nearly equals to 0. Understood this one? Okay. So I must give it sufficiently enough energy so that it comes out here. And when it comes out here at zero field or maximum potential or near about zero potential, okay, after this point, what will happen? The moon will automatically pull the body towards itself, isn't it? Imagine a ball going towards hill. Okay, what is the minimum energy that I must give so that it reaches out here? The minimum energy that I must give is this much, isn't it? This much energy. Okay, and this much energy is nothing but minus gm by r minus energy at this point or potential energy at this point, and potential at this point is nothing but zero or nearly equals to zero. Okay, if these things are ignored, that means these two planets are very far away. That means the potential out here will be nearly equals to zero. You can plug in the equation and see it for yourself. Okay, so the potential or the energy required to take the satellite from this point to a point where field is equals to zero. Okay, out here field is equals to zero is nothing but this much amount of energy. And after this point has been crossed, I require some more amount of energy. And why do I require that energy? Because this satellite has to reach this planet or surface of the moon with zero velocity. That means if I leave or if I stop giving energy to the satellite out here, what will happen? It will increase its velocity down, and it will crash land into the moon, isn't it? It will smack into the moon, and I do not want that. So from out here to out here, I must give it sufficient energy so that while coming out here, the velocity becomes zero, isn't it? Understood this much? Okay, so whatever is the velocity out here, the velocity out here becomes zero. Okay, so no amount of energy or no amount of kinetic energy is there to the satellite when it reaches at this point. So first, let us expend some energy to send the satellite from the surface of the Earth to a point where field is equals to zero or potential is equals to zero. Okay, so minimum work done or work done by propulsive force or work done by external force. Work done by propulsive force is nothing but zero. Okay, or potential energy at this point minus gm by r, or final potential energy minus initial potential energy, isn't it? This is nothing but gm by r, gm by r. Okay, and this work done I'm finding it for 1 kg. Later when I multiply the entire thing by mass of the satellite, I'll get for the work done for mass of the satellite. That is for another thing, but I'm taking out here what is the work done for 1 kg of cloth. Okay, to send it out here at the point of zero field or maximum potential or zero potential. Understood? Now from here to here, I have to supply it some work. After the satellite has reached this point, I have to supply this amount of energy to slow it down. No? Because if I don't give this amount of energy, the satellite would crash land into the moon. And what is this amount of energy? This amount of energy is nothing but final potential minus initial potential, isn't it? And this amount of energy is nothing but minus gm by r minus zero. Okay, and I must give it this much amount of energy. Okay, otherwise what would happen? It would crash land into the moon with this much amount of kinetic energy. Okay, minus gm by r. So I do not want that. So I must give it this much amount of required or energy required. This energy in, forgot the spelling of energy required to reach the point of zero gravitational field or highest potential energy or point of highest potential energy. All are the same thing. Point of highest potential energy. NERGY. I'm forgetting a lot of spelling today. Or point of zero potential energy. Okay, this is the amount I must give the satellite to reach out here. Okay, and this much amount of energy is nothing but gm by r minus zero, zero minus gm by r, isn't it? So this much amount of energy I must supply to stop the velocity or stop the kinetic energy when it reaches the moon. Okay, plus gm by r, g into mass of moon by r, plus g into mass of moon by r. Okay, energy given to satellite to slow it down, Take this similar to a problem of mechanics where a ball is out here and it must reach a point out here. So this is the amount of energy I must give it to reach the top of a hill. Okay, and after it reaches the top of a hill, it will roll down. So in order to prevent it from going out here or crashing out here, what I must do, I must reduce some amount of velocity out here, or I must give it some opposite pull or opposite force, isn't it? So that much amount of energy is nothing but gm by r or potential energy out here. Okay, so this much amount of energy is given it to reach the topmost point, and this much amount of energy is given it to slow it down. Okay, so our total work done is nothing but work done by propulsion energy is nothing but gm by r plus gm by r. Or if I take g common, it is nothing but mass of earth by radius of earth plus mass of moon by radius of moon. And this is the answer that is given. And this is actually the correct explanation. Okay. Now there is an actual question that came in your JEE Advanced. Okay. The question is such like, okay, what is the minimum velocity required to reach the moon? Okay. So there it is Earth. And a spacecraft is at the surface of Earth. And here it is moon. Okay. What is the minimum velocity required for the satellite to reach the moon? Okay. Out there, okay, in that question, there was no requirement for the moon to reach with zero velocity at the surface. Okay. So the amount of energy I require is not only this much, isn't it? From the surface of Earth to a point where the field is zero or the potential is maximum, isn't it? This is the only amount of energy I require. And that was the question. In that question, there is some other assumption. See, in this question, or where I have done the potential at maximum, potential at zero field is equals to zero. In this question, I have assumed that the Earth and Moon are very far away. Okay, and that is why the potential at the point where field is equals to zero tends towards zero. That means this distance is very small. Okay, or nearly equals to zero. But in this question, okay, in this question, the distance between Earth and Moon are not neglected. That means what? That means out here it would have a non-zero potential. So it would not be zero minus something. It will be potential at this point, or potential at a field, or potential at a point where field is equals to zero minus potential at surface. And what is this much? This much would be nothing but, see, for this question, this situation is nothing but work done by propulsion is nothing but this much, or potential at final point. What is the potential at final point? Potential due to Earth plus potential due to Moon, isn't it? So minus g mass of Earth by this much distance minus g mass of Moon by this much distance, or center of Moon to this point, center of Earth to this point, isn't it? So potential at this point where the field is equals to zero is nothing but minus gm by x. Let x be this point where field is equals to zero minus g mass of Moon by y. Potential due to Moon at this point where field is equals to zero. Understood? And this point was nothing but exactly this point. Okay, where field is equals to zero. Okay, out there, because the Earth and Moon are so close, this point would have a potential energy this much. Okay, this has a very low value because x is very large distance and y is also very large distance. So it would have a very low value, a negligible amount of magnitude. Okay, if the Earth and Moon are sufficiently far apart, this would tend towards zero. Okay, so this potential at final point, okay, potential at final point minus potential at the surface, minus potential at the surface, gm by r. This is the amount of energy required for a satellite to on the surface of the moon to reach the moon. Because after this point, I do not need to give the satellite any more amount of energy, no? Because in that question, or in this question, there is no requirement for the satellite to reach with zero velocity. So the amount of energy I must give the satellite is from this point to this point, or from surface of Earth to a point where field is equals to zero, isn't it? So this much is the amount of energy required. Now out here also, this distance, okay, because potential at the surface of Earth is not exactly minus gm by r. It is minus gm by r minus gm by distance from center of moon to the surface of Earth. Even in this question, okay, that potential is ignored. Even in this question, minus g mass of moon by some distance, okay, this value is ignored. Understood? So this is the amount of energy, or minimum amount of energy I must give a satellite to reach the moon. Okay, because all my energy is expended in taking the satellite from this point to a point where field is equals to zero. Okay, now minus g m by x minus g m by, or g mass of moon, small m is mass of moon, okay, g m by y plus g m by r. G m by r is nothing but the radius of Earth, and the capital M is nothing but mass of Earth. Understood? Fair and fine. So this is the amount of energy I must give the satellite. Now the question was required for minimum velocity, no? It was asking for velocity, not the amount of energy. I can simply apply kinetic energy is equal to this much energy, isn't it? The kinetic energy that I give to the satellite to take it out here is nothing but the gravitational potential energy it must overcome, isn't it? So kinetic energy half mv square is equals to minus gm by x minus gm by y plus gm by capital R. And the v out here was nothing but the minimum velocity that was required. We have to find out this v. Just solve the PYQ. Okay. Achha, one more important thing. Okay. Out here I was working with potential. To find out the work done, okay, you have to multiply the entire thing by mass of satellite. This mass is nothing but mass of satellite. Okay. So out here work done would be nothing but this entire term into mass of satellite. This is nothing but potential, or work done on 1 kg. Okay. Similarly out here, we have written the answer. This is nothing but work done on 1 kg. So if you multiply this, total work done is equals to work done on 1 kg multiplied by mass of satellite. Even out here, in the main answer. Okay. Out there I have already multiplied by mass of satellite. So it doesn't make a difference. Understood? So I was working with potential. Okay, the graph was for potential. The graph was for potential. I was working with potential. Okay. Now this question is very interesting. Okay, just see the question. Out here there is sun. Okay, and Earth revolve around it. Okay, Earth is revolving around the sun. The radius of Earth orbit is nothing but r. Okay, this is the radius of Earth's orbit, r. The question is asking, what is the minimum velocity that I must give a satellite sitting on the Earth's surface such that it escapes the solar system? That means what is the necessary condition to escape the solar system? To escape the gravitational pull of the sun. Because in our solar system, if you escape the gravitational pull of the sun, you will escape the solar system. Understood? This is the main star of our solar system. Fair and fine. So what is the minimum velocity that I must give this satellite such that, okay, such that it reaches the or it escapes the solar system? Fair and fine. Okay. So I want to simplify this question in a much simpler manner. Okay. Let's break down this question. This is sun out here. Okay. Sun out here, and this is the orbit of Earth. That means Earth rotate around the sun in this orbit or in this circular orbit. Okay. Now let us first make us disappear Earth. Okay. Suppose there is no Earth and there is a satellite of mass n. Okay. Of mass n revolving around the sun. Okay. This satellite of mass n is revolving around the sun. There is nothing else in this orbit. Okay. My first question is, what is the velocity of this orbit? Okay. Let's name the variable also. N is nothing but mass of satellite. Small n, I'm going to use another small n variable, which is nothing but mass of Earth. Mass of Earth. And another variable, capital M, which is nothing but mass of sun. So do not get confused between these variables. Mass of sun. Capital M is nothing but mass of sun. Small m is nothing but mass of Earth. And n is nothing but mass of satellite. So my first step is, suppose let us make the Earth disappear for a second. A satellite is rotating in this orbit. The orbit is exactly as the orbit in which the Earth rotates around the sun. Okay. What is the velocity of this orbit? The velocity of this orbit or orbital velocity is nothing but g m by r, or g into mass of sun by radius of orbit. Isn't it? Now my next question is, or v naught is nothing but orbital velocity. Orbital velocity of Earth. Velocity of Earth around sun. That means for the satellite to stay in this orbit, must rotate or evolve in orbital velocity or evolve with orbital velocity, isn't it? Now my next question is, what is the minimum velocity that I must give out here? Okay, so that this satellite escapes the gravitational pull of the sun. Okay, my question can be different as, what is the escape velocity from this orbit? The escape velocity from this orbit is nothing but v escape from sun's orbit or from this orbit. Okay, v escape from this orbit is nothing but under root of 2 gm by r. 2 gm by r. That means what? If there is any particle in this orbit, okay, and that particle has this velocity or greater than this velocity, that particle will escape the gravitational influence of the sun. This much is understood. Okay, at this distance from the sun, any particle out here in this orbit, okay, that has this velocity or velocity greater than this velocity will escape the gravitational pull of the sun. Understood? That is velocity of escape out here at this distance. Now this satellite was already orbiting with v naught, no, or under root gm by r. What is the additional velocity that I must give the satellite so that it attains the escape velocity? So additional velocity that must be given. Additional velocity that must be given to satellite. That must be given to satellite. And why must I give this additional velocity? To make this satellite take out of the solar system, or to take this satellite out of the solar system. That means I must give it enough amount of velocity such that it overcomes the escape velocity. Okay, or becomes equals to the escape velocity. So additional amount of velocity that must be given is nothing but delta v, which is nothing but the additional amount of velocity, is nothing but escape velocity minus the velocity it already had, isn't it? And to optimize my thing, my additional velocity must be applied in the same direction as the direction of the velocity in the orbit, isn't it? Understood? if I give my additional velocity in this direction, it will be much easier, no? Isn't it? Because the vectors of the velocity gets added directly. So I'll much quickly reach the escape velocity, isn't it? So additional velocity is nothing but 2 gm by r, which is the escape velocity, minus the velocity it already had, gm by r, because it was rotating in the orbit. So this is nothing but the escape velocity at this point or at this orbit, okay, minus the orbital velocity. This is the additional velocity. This is the additional velocity I must give the spacecraft or satellite so that it reaches out of the solar system. Okay, let's rearrange these values. This can be written as root 2 into under root gm by r minus under root gm by r. Okay, I can take gm by r common, or it can be written as under root gm by r into root 2 minus 1. Root 2 minus 1. This is the additional amount of velocity. And gm by r is nothing but orbital velocity. So this can also be written as v orbital into root 2 minus 1. So this much amount of additional velocity must be given to this spacecraft so that it escapes the solar system. Now what I have to do is I have to calculate in terms of energy. Okay. So why are you doing that? Because in our original question, the satellite was not in the orbit. Okay. Earth was around the orbit in the sun, and this Earth contains the satellite. So actually you have to launch this satellite from Earth itself. Okay. There is another gravitational pull of Earth. So that equation you have to take in factor. So to make the process easier, we'll calculate our terms in terms of energy. Okay. So the additional velocity, okay, the additional velocity that I must give this satellite is nothing but v0 into root 2 minus 1. Understood this much? Okay. Now this velocity or the additional velocity, how can I describe this velocity in terms of kinetic energy? So kinetic energy that must be given, okay, or additional kinetic energy. Additional kinetic energy is nothing but half into mass of satellite into the velocity that must be given, isn't it? The velocity is nothing but this value square. Half mv square is the formula for kinetic energy, no? So half m into v square. So this is the amount of kinetic energy that I must give this satellite to make this satellite escape from the orbit. Okay, understood this one? So any satellite, okay, that has this much amount of additional energy, okay, that means any satellite that is rotating around the sun, okay, in this orbit, if I give this much amount of kinetic energy or this much amount of additional kinetic energy, it will escape from the Earth's orbit, or sorry, it will escape from the sun's orbit. Okay, this much is known. Okay, so understand this point up till here very nicely. This is the amount of kinetic energy that I must give this satellite, okay, so that it escapes the sun. Fair and fine. Now in our original question, the satellite was not revolving around sun. Earth was revolving around sun, no? And the satellite was kept in top of Earth, isn't it? Okay. So when Earth is revolving around sun, the orbital velocity of Earth is already with the orbital velocity of satellite. No? This much is understood. Now just look at Earth. Okay. Suppose I am launching with velocity v. Okay, I'm launching this. This was Earth. Okay. On top of Earth, the satellite was kept stationary. Okay, and the satellite and Earth was moving in this circular orbit with orbital velocity. Okay, orbital velocity is equal to under root g mass of sun divided by r. This much r. Okay, so satellite was kept Earth and it was rotating with orbital velocity. Now this satellite is launched with velocity v. I don't know the value of velocity v, but that velocity v is sufficiently high such that this satellite has to escape the solar system, or this satellite has to escape the gravitational influence of the sun. Understood? Initially, the satellite was stationary in top of Earth or was sitting on the surface of Earth. Finally, as soon as I give it some velocity, okay, what will happen? This velocity is supposed to take this satellite away from the sun's influence or away from the solar system. So initially, the potential, there was some energy, but as soon as the satellite was given a velocity v, okay, suppose some explosion occurred and satellite suddenly constituted velocity v, okay. So suddenly, if I given satellite the velocity v, what is the exact amount of energy this satellite contains at the moment the velocity was provided? Okay, energy contained by satellite, energy contained by satellite after giving velocity, after providing it with velocity, giving it with velocity v, and this velocity v is supposed to be the minimum velocity that is supposed to take this satellite outside the solar system. So I'll calculate the total energy of this satellite or total gravitational energy or total energy of this satellite. Okay, after it has been provided with velocity v. So energy is nothing but half mass of satellite into v square. Okay, and on top of what this was sitting on top of what, no? Okay, so out here the gravitational potential of the earth should be included, no? See, minus g m by g mass of earth into mass of satellite by radius of earth. So this much amount of energy is the energy contained in a satellite, okay, when it was being provided with the velocity v, and that velocity v is supposed to take the satellite away from the solar system. Now you might have some another doubt, sir. Why isn't the gravitational potential energy of the sun considered out here? See, the earth is already sorry, the satellite is already sitting on top of earth, no? And the earth was moving in this orbit, isn't it? So the all the energy that was contained in the earth, or the potential energy of earth and kinetic energy of earth, is already included in the satellite, no? And you have to find out velocity from the frame of reference of earth, isn't it? So you won't be calculating sun. Okay, understood? See, out here, see, in this equation, what did you do? In this equation, you are already considering, this equation takes the energy consideration of the sun, isn't it? Okay, and out here the satellite was sitting on top of earth, so whatever energy consideration was taken for satellite is already included in earth, no? Earth also has the same energy, isn't it? Okay, so this energy consideration was already, or this energy consideration was already taken in factor. That's why you are not adding the parameter of minus g mass of sun divided by capital I. Okay, this is the total energy of the satellite on top of earth's surface after velocity v was provided, this much. Okay, and this is the energy required for a, or this is the energy required for a particle to take anything out of the solar system. Okay, now listen to me carefully. Can I say this amount of energy is equals to this amount of energy? See, if the total energy out here as soon as it was launched is greater than equals to this amount of energy, then only the satellite will escape the solar system, no? The total energy the satellite had after it attains the velocity v should be greater than this energy required to escape, greater than or equals to, then only it will escape the solar system. And once you have understood that this equation or this energy will be greater than equals to this energy, then your equation is solved. Now the meaning of the question is nothing but equation solving. So what am I saying? This energy is greater than equals to this energy. Okay, or see, let's copy those things. This energy. Okay, let's copy this thing. Okay, and let's copy this thing also. Let's copy this thing also. Okay. All I said was this energy should be greater than equals to this amount of energy. So I can easily say that half in v square, or v is nothing but the escape velocity with respect to earth's surface, minus g m n by r is equals to half n into v naught into root 2 minus 1. Okay, whole square. Now as soon as you solve the equation and find out the value of v, this value of v is nothing but the escape velocity that is required in the question. Okay, escape velocity from earth to take it out of the solar system. Understood? Cancel out the n. Okay, just solve this equation. V naught is nothing but under root gm by capital R, g capital M by R. Okay, and solve for v. Okay, I believe you can do it yourself. See, just solve it yourself. Okay, and with this we come to the end of our lecture of gravitation. From the next class we'll start with rotational mechanics, the core of rotational dynamics. We already gave you some rotational mechanics in vertical energy theorem. Okay, after this we'll start with core of, or dynamic core of rotational mechanics. Okay, that's it.